Hello, my name is Andrea Correia. I will be presenting OrcGC Automatic Lock-Free Memory Reclamation, a work done by myself, Pedro Ramalhete and Pascal Felber. I will start by introducing some definitions. A global reference is a reference stored in a variable that is always accessible by all threads in the system. A local reference is a reference only accessible by a single thread. An hard link is a reference to a shared object that is stored in another shared object. An unreachable object is an object that cannot be accessed through a global nor local reference. Here is the code for Michael and Scott lock-free queue, where we can see the global references, the hard link, and the local references. An example where we have multiple nodes inserted in the queue, we can see that C, D, and E are reachable nodes, but A and B can be later deleted. I will start by presenting the memory reclamation scheme past the pointer. Like other lock-free schemes, past the pointer implements two methods. The method getProtect that must be used by a thread to protect an object before dereferencing it, and the method retired, called when an object has no hard links that refer to it. After retired, the object is deleted when it becomes unreachable. The getProtected method is implemented in the same way as in hazard pointers scheme. The difference is in the retired method. PTP uses an array of hazardous pointers where each entry is assigned to a thread and an array of handovers shared by all threads. For each hazardous pointer entry, there is an associated handovers entry. On the hazardous pointers array, it is stored the address of an object that was previously protected. The handovers array is where a retired object is placed if there is an hazardous pointer to it. Now I will show an example where thread T0 will retire A. The thread will start by searching for A in the hazardous pointer. It has located A on thread 1 and replaces on the handovers array what was previously there with A. Because it is null, it stops the execution of the retired method. Now I will give an overview of OrcGC, our automatic memory reclamation. To reclaim memory, OrcGC must detect when an object becomes unreachable. For that, it combines per object reference counting with a pointer-based reclamation scheme. The reference counting is used to count the number of hard links to the object, and the pointer-based reclamation scheme tracks the local reference to the object. OrcGC integrates PTP as its pointer-based reclamation scheme. It provides linear bound on unreachable objects for algorithms that do not form chains of unreachable objects. In case there are cycles of unreachable objects, that memory will be leaked. OrcGC has lock-free progress. In order to track the number of hard links to a shared object, every shared object must extend OrcBase. OrcBase has a member _orc, and that's the variable that keeps the counter. _orc is composed of the first 22 bits, where the counter is kept, after the 1 bit that indicates if the object is marked to be deleted, so if the object is retired, named BRetired, and the remaining bits is where the sequence is stored, and the sequence changes every time the counter, the first 22 bits, change. If the counter, the first 22 bits,
is OrcGC, it indicates there's no hard links to the object. All shared variables must be declared OrcAtomic instead of stdatomic to allow the Orc variable to be updated every time an hard link changes. We can see an example, for example, of the compare and swap operation, that it is first the root pointer is pointing to object A and will change to refer to object B. This means one less hard link to object A and an extra hard link to object B. Also, every time a shared object is created, it must be by calling make arc. Every time an atomic load or make arc is called, the local reference it returns is automatically protected by an hazardous point. These operations will return an OrcPTR object that will include the local reference and the index where the hazardous pointers of this reference is kept. This is an example on how to annotate Michael and Scott Q with OrcGC. So the node must extend OrcBase. Every time a new node is created, instead it must call make arc. The next and add and tail that are hard links must be changed from stdatomic to OrcAtomic. And every time a load is called, it is stored in an OrcPTR object. Regarding object deletion, I will show an example. T3 will start by dequeuing node A, B, and C. At this point, the global references add and tail no longer can reach A, B, and C, but these nodes are still reachable through T2 that has a local reference to it, to node A. The only node that can be retired at this point is node A that has Orc at 0, but cannot be deleted. There is still another pointer published in for node A at T2. Once this local reference disappears, then node A can be deleted. And to validate this, the Orc must be at 0 at the start of the traversal of the hazardous point and at the end, and the sequence associated with the Orc cannot change. Once this is validated, then node A can be deleted, and when the deletion is called, it will call the destructor of A, that in turn will remove the hard link to B, that will cause the Orc of B to reach 0, that then will be retired, and so on. This could cause a stack overflow. To avoid this, our implementation, instead of calling recursively the retire, will put the objects in a retired list, local retired list, that to be later scanned for all those objects. And because this can happen, for chains of objects that become unreachable, we cannot guarantee a linear bound. Here you can see the results for Michael and Harry's log-free linked list. In conclusion, OrcGC is an automatic memory reclamation that can be used in acyclic algorithms. It can show 50% decrease in performance when compared with memory reclamation schemes. On the other hand, it requires simple annotation of the algorithms, and it can be the only solution for complex algorithms. It provides linear bound on the number of unreachable objects, and it can be used with any allocator and C++11 compiler.